The fault that broke off the southern Philippines today is not the fault that seismologists have been warning about. That should be reassuring. It is the opposite. A magnitude 6.3 struck offshore of Sarangani this afternoon, and the first official bulletin got the size wrong by a factor of 11 and the location wrong by 160 miles. When the corrected solution finally came in, it carried a single number that almost nobody has reported, and that number proves this was not the June 8th rupture failing again. This was something shallower sitting above it, loaded by June and failing on its own account. Which leaves the harder question. If the stress has started moving, what exactly is it moving toward? Before we go any further, if you enjoy what we do here at Project Nightwatch, hit like and subscribe so you don't miss any of our nightly debriefs, and drop a comment and tell me where you're watching from tonight. Now let's get into it. Part 1. The quake that arrived twice. At 14 minutes past 12 in the afternoon, Philippine Standard Time on Wednesday, August 5th, 2026, the seafloor off the southern tip of Mindanao broke. The waves from that break reached the nearest seismometers in seconds. They reached stations across the Philippine archipelago within a minute. They reached the global network within a few minutes more, and somewhere in that window, an automated system did what automated systems are built to do. It looked at the earliest arrivals it had, it solved for a location and a size, and it published an answer. That answer was wrong. The first bulletin from the Philippine Institute of Volcanology and Seismology, the agency everyone in the country calls PHIVOLCS, estimated the magnitude at 7.0. It placed the epicenter roughly 258 kilometers, about 160 miles, south-southeast of Sarangani, out near the Talud Islands. That position is not really Philippine water in any practical sense. It is effectively Indonesian water, on the far side of a channel, on a different piece of the plate boundary entirely. Then more data came in, and the picture did not get refined. It got replaced. The reviewed solution moved the earthquake back north, to a point 37 kilometers, about 23 miles, southwest of Balut Island in the municipality of Sarangani, in the province of Davao Occidental. It dropped the magnitude to 6.4, and when the moment tensor was published a little later, that solution did something the first bulletin could never have done. It told us exactly which fault plane had moved. Here is the part that matters, and I am going to say it now rather than making you wait 2 hours for it, because the rest of this is the evidence for it. The fault that moved today is not the fault that seismologists have been warning about. That is not a small statement. There is a specific stretch of this plate boundary that scientists have been pointing at since June, a segment they can name and measure and put a length on, a segment that has not released anything in more than a century. And today's earthquake, which arrived in the same region, inside the same sequence, on the same subduction system, did not touch it. So let us get the numbers on the table properly. The reviewed PHIVOLCS solution puts today's earthquake at magnitude 6.4 at a depth of 13 kilometers, which is about 8.1 miles, epicenter 37 kilometers southwest of Balut Island. Tectonic in origin, which is the agency's way of saying this was plate motion, not volcanic. The United States Geological Survey has it slightly differently, which is completely normal. Their solution is magnitude 6.3, depth 10 kilometers, about 6.2 miles, with the epicenter roughly 32 kilometers, 20 miles, southwest of Sarangani. They assigned a green alert, which is the lowest tier on their impact scale, and they did not raise a tsunami flag. The European Mediterranean Seismological Centre listed the depth at 35 kilometers. 3 agencies, 3 depths, 10 kilometers, 13 kilometers, 35 kilometers, and that spread is not sloppiness. Depth is genuinely the hardest parameter to constrain in an earthquake solution, and it is the one agencies disagree about most often. The reason is geometric. To pin down how deep an earthquake was, you want stations sitting more or less directly above it, because those are the stations where the travel time changes fastest as you move the source up or down. When an earthquake happens offshore, nobody has a station above it. Everybody is off to one side on land, and from off to one side a shallow earthquake and a slightly deeper one produce very similar arrival times. So the solutions drift, and you get 10, 13 and 35 from 3 different processing centres looking at the same event. Hold on to that spread, because depth is going to turn out to be the single most important number in this entire story, and it is also the number nobody has been reporting. At 26 minutes past 4, Coordinated Universal Time, 12 minutes after the earthquake, the National Oceanic and Atmospheric Administration issued a tsunami bulletin for Mindanao. I want to be precise about what that bulletin does and does not say, because this is exactly the kind of thing that gets amplified into something it is not. The bulletin was issued. It carries no warning status. It carries no impact details. There is no confirmed damaging tsunami from today's earthquake. If you see a post telling you otherwise, it is running ahead of the data. The shaking itself was reported the way FIVOLX always reports it, on the Philippine intensity scale town by town. Intensity 5 described as strong shaking, in Glan, in Sarangani province. Intensity 4, moderately strong in Kiamba and in General Santos City. Intensity 3, weak, in Masim and Malapatan in Sarangani and in Lake Cebu in South Cotabato. Intensity 2, slightly felt, in Banga and Surala, further out in South Cotabato. The USGS ran their own estimate and put the maximum shaking at modified Mercalli 6. And it is worth walking through what a 6 actually means on the ground, because intensity scales are descriptions of human experience, not measurements of the earthquake. At modified Mercalli 6, everybody feels it. Nobody's unsure whether that was an earthquake. Objects come off shelves, pictures come off walls, furniture moves, plaster cracks. Poorly constructed buildings may take real damage, and I want you to hold on to that phrase, poorly constructed buildings, because we are going to come back to it and it is going to matter more than it looks like it matters right now. Well-engineered structures usually perform much better at intensity 6. They shake, people are frightened, and they stay up. The green alert from the USGS deserves a sentence too, because people see the word green and read it as an all clear, and that is not quite what it means. That alert comes out of an automated impact estimation system that takes the shaking model, overlays it on population data and building stock data for the affected area, and produces a probability distribution for fatalities and for economic losses. Green is the lowest tier. It means the most likely outcome is no deaths and limited losses. It is a forecast generated by a computer from a shaking estimate that was itself generated by a computer, using assumptions about how the buildings in that area are constructed. Everything about that chain is reasonable. Everything about that chain is also an average, and averages have a way of being wrong in exactly the places where the local situation is unusual. Remember that, because the local situation in southern Mindanao right now is extremely unusual, and we are going to come back to it. And the phrase tectonic in origin, which FIVOLX attaches to almost every bulletin, is doing quiet work as well. It is the agency saying, up front, that this was plate motion. Not a volcano, not a collapse, not anything exotic. On an island that has active volcanoes, that distinction gets made explicitly so that nobody has to guess. It will turn out that the physics backs that statement up to a degree most bulletins never bother to demonstrate, and we'll read that evidence directly a little later. So that is today. A strong earthquake, shallow, offshore, felt across the southern end of Mindanao, with a first bulletin that was wrong in almost every particular, and a second one that was right. But none of that is why this event is worth 2 hours of your evening. This earthquake did not happen in a quiet place. It happened inside a sequence that has been running for nearly 2 months. On June 8th of this year, a magnitude 7.8 struck offshore of southern Mindanao. It killed people, it brought down buildings, it generated a tsunami, and since that day, the crust underneath this part of the Philippines has been in a state of continuous readjustment, producing thousands upon thousands of aftershocks, several of them large enough to be significant earthquakes in their own right. So when a strong quake hits the same region 2 months later, there are only a few possible stories, and they lead to very different places. 1. This is a routine aftershock. The sequence is decaying the way sequences decay, and in 6 months nobody will remember today. 2. This is the same fault patch failing again, which would mean the June rupture did not finish what it started. 3. This is something else in the same system, loaded up by June and now failing on its own account, which would mean the stress is moving. The moment tensor answers that question. It answers it cleanly, it answers it unambiguously, and the answer is not the one most coverage has assumed. But before we can read the mechanism, we have to fix the geography. Because 2 different places in southern Mindanao carry the same name, and almost every headline written about this earthquake today has quietly conflated them. Part 2. 2 places with the same name. In June, the headline said an earthquake had hit Sarangani. Today, The headline said an earthquake had hit Sarangani. Those are not the same place, and the difference between them is about 100 kilometers, roughly 62 miles of plate boundary. This trips people up constantly, and it is not their fault, because the Philippines genuinely has two administrative units in southern Mindanao carrying the name Sarangani, and they sit in different provinces. The first is Sarangani the province. It is in the Sox-Ksarjan region, immediately adjacent to General Santos City, which is a city of something like 722,000 people on the southern coast of Mindanao. This is where June's devastation was concentrated. This is where Glan sits, the town that reported intensity 5 today. When you read about the June 8th earthquake and the deaths and the collapsed structures, you are reading about this Sarangani. The second is Sarangani the island municipality. It sits in the province of Davao Occidental, considerably further south, out where the land runs out and the archipelago starts breaking up into islands. The municipality is made up of Balut Island and Sarangani Island. Today's epicenter, by the FIVOLC solution, is 37 kilometers southwest of Balut Island. Same name, two provinces, about 100 kilometers apart. Now, 100 kilometers might not sound like much when you are looking at a map of the whole Pacific. On a subduction margin, it is a great deal. It is enough to put you at a different position along the trench axis. It is enough to change the depth to the plate interface underneath you, because that interface is a ramp, and moving along it changes how far down the contact surface is. It is enough to put you on a different segment of the fault system, with a different rupture history and a different stress state. It helps to build the picture properly, because everything in the second half of this video depends on it. Where two tectonic plates converge and one dives beneath the other, the boundary between them is not a vertical crack. It is a surface, and that surface descends at an angle. At the trench itself, where the descending plate first bends downward, the contact between the two plates is close to the seafloor, only a few kilometers below it. Move landward, and the contact deepens. 10 kilometers inland it might be a few kilometers down. 100 kilometers inland it might be 40 or 50 kilometers down. It is a ramp, and you are standing on the roof of it. So the position of an earthquake along that ramp tells you something specific. A shallow earthquake near the trench is on a different part of the contact surface than a deeper earthquake further inland, even if both of them are on the same fault. They are on the same structure at different depths, and those depths behave differently. The shallow near-trench portion sits in soft, water-saturated, poorly consolidated material. The deeper portion sits in stiffer rock under enormous confining pressure. They fail differently, they generate different kinds of shaking, and they produce very different tsunamis, which is a point we are going to build an entire section on. That is why 100 kilometers of separation along the coast is not a trivia detail. It puts you somewhere else on the ramp. So when today's earthquake is described as hitting Sarangani, and June's earthquake is described as hitting Sarangani, the natural reading is that the same patch of ground got hit twice. That reading produces one of two wrong conclusions. Either you think this is obviously the same fault failing again, which is the assumption a lot of coverage made today, or you think correctly that these are different places, and then you assume they must be unrelated, which is also wrong. The truth is in between, and it is more interesting than either. Today's earthquake is not at the June epicenter, it is well south of it, but it is inside the aftershock zone of the June rupture, which is enormous, and it is on the same subduction system, and the mechanism ties it directly to what happened in June. It is related, and it is somewhere else. That combination is exactly what makes it worth talking about, and it is exactly what gets lost when both events get filed under the same place name. The reporting problem compounds from there. News desks work from bulletins, bulletins carry place names, and place names get copied forward. Once the first wire story says Sarangani, every subsequent story says Sarangani, and nobody stops to ask which one, because the name resolves fine in a headline. Readers who followed June closely then map today's event onto the mental picture they already built 2 months ago, which is centered on General Santos and the towns around it. That mental picture is roughly 100 kilometers off. It is off in a direction that matters, and it is off in a way that makes the two events look like one event repeating rather than one system expanding. And the reverse error is just as common. Somebody notices the province is different, concludes the two events are unrelated, and files today under coincidence. On a plate boundary this active, coincidence is a genuinely reasonable default. Southern Mindanao produces significant earthquakes regularly enough that two of them 2 months apart do not automatically belong to the same story. The mechanism is what settles it, and it settles it in favour of connection. There is a human version of this too. Imagine somebody standing in Glan. In June, they experienced intensity 8 shaking, which is violent. Furniture overturns, chimneys fall, weak structures are badly damaged. They know people who died. Today they felt intensity 5, strong shaking, enough to be genuinely alarming in a town where every wall already has cracks in it. And both events were reported to them under the same name, in the same phrasing, as though the earth had returned to finish something. It did not return. It moved. That distinction is the spine of everything that follows, because the entire question in this story is where the stress is going, and you cannot answer a question about where something is going if you cannot say precisely where it has been. So we have the location fixed, 37 kilometres southwest of Balut Island, in the island municipality, in Davao Occidental, at the southern end of a very large aftershock zone. That is half of what the review corrected. The other half was the size. And that correction was substantially bigger than it appears because of the way the magnitude scale works. Part 3. How a bulletin moves an earthquake. 160 miles. 258 kilometres. That is not a refinement. That is not somebody nudging a decimal point. 160 miles is the distance from Philadelphia to Boston. It is the difference between an earthquake in Philippine territorial water and an earthquake essentially in Indonesian territorial water on a different segment of a different trench, with different implications for who needs to worry. And it happened on review, in the space of maybe an hour. I have looked at a lot of automatic solutions and I have watched a lot of them get corrected. I have not often seen one corrected by that much. So it is worth understanding exactly how a system produces an error of that size, because the explanation is not incompetence and it is not concealment, and once you understand it you will never read a first bulletin the same way again. Start with what an automatic solution actually is. When an earthquake happens, seismic waves radiate outward and hit stations at different times depending on how far away each station is. If you know the arrival times at enough stations, and you know how fast waves travel through the rock in between, you can solve backwards for where and when the rupture started. That is the whole trick. It is triangulation with sound. An automatic solution runs that calculation the moment it has enough arrivals to attempt it, with no human in the loop. It does not wait for the best stations. It does not wait for the most useful stations. It waits for the fastest stations, which is a completely different set. Then it publishes. And it publishes on purpose, labelled as automatic, because in a country with a tsunami-capable coastline, the difference between an answer in 4 minutes and an answer in 40 minutes is measured in lives. Speed first, accuracy second, is not a flaw in the design. It is the design. Now here is where the error comes from, and it has a name: azimuthal gap. Picture the epicenter with a circle drawn around it, and picture where the reporting stations sit on that circle. If they are spread all the way around, you have information coming from every direction, and the solution is boxed in on all sides. Move the trial location any direction, and the fit gets worse immediately, so the algorithm converges tightly on the right answer. Now picture an offshore earthquake in the southern Philippines. Every land station is on one side, the other side is open ocean, and there is nothing out there. So instead of a full circle of information, you have an arc, maybe a third of a circle, all of it in one direction. Across the array, the solution is well constrained. Along the axis pointing away from the array, out into the empty ocean, it is barely constrained at all. What that means in practice is that the algorithm can slide the trial epicenter a very long way out, along that unconstrained axis, and the arrival times still fit almost as well. The misfit curve, instead of being a sharp valley with steep walls, is a long, shallow trough, and a solver looking for the bottom of a long, shallow trough will happily settle hundreds of kilometres from where the earthquake actually was, and report it with a straight face, because by the mathematics it is a legitimate answer to the question it was asked. Add sparse early arrivals, add a few noisy picks, and you get an epicenter out by the Talod Islands for an earthquake that happened off Balut Island. There is a compounding problem too, and it is worth naming because it explains why the location error and the magnitude error travelled together rather than separately. Location and magnitude are not computed independently. To convert ground motion at a station into a magnitude, you have to correct for how far the waves travelled, because amplitude falls off with distance. Get the location wrong by 258 kilometres, and every distance correction in the calculation is wrong by that much as well. In this case, the algorithm believed the earthquake was much further from the recording stations than it actually was, which means it believed the waves had spent much more of their energy getting there, which means it inflated the source to account for motion that was never attenuated in the first place. One bad location does not produce one bad number, it produces a cascade, and that is why the two corrections arrived together. The review did not fix the position, and then separately discover the magnitude was off. It fixed the position, and the magnitude fell out of it. The magnitude overshoot has its own mechanism, and it is worth a minute because it explains something we will need later. Early automatic magnitudes are usually amplitude-based. You measure how big the ground motion was at a station, you correct for distance, and you get a number. That works well for moderate earthquakes. It works badly for large ones, because of a problem called saturation. The instruments and the measurement bands used for rapid estimates respond to a particular range of frequencies, and a genuinely large earthquake radiates a lot of its energy at frequencies below that range. So the estimate climbs, and then it stops climbing, and above a certain size it stops tracking reality altogether. Push a big, long-period arrival through a fast amplitude algorithm, and it can hand back a number that is well off in either direction, depending on exactly how the mismeasured location and the mismeasured distance correction interact. The reviewed solution used something better. It used the W phase, which is a long-period signal that arrives between the first compressional wave and the main surface waves. The W phase moment tensor is a fundamentally more robust estimator of size, because it is measuring the actual seismic moment, the physical quantity of how much rock moved, how far over how large an area, rather than inferring it from peak wiggle amplitude. It takes longer to compute because it needs a longer stretch of the record. It is worth waiting for. Now, I know exactly what this looks like from the outside, and I want to deal with it directly. From the outside, it looks like this. An agency announced a magnitude 7. Then quietly an hour later that 7 became a 6.4 and the earthquake moved 160 miles, and the whole thing stopped being a headline. If you are already inclined to believe that agencies manage information rather than report it, that sequence is going to look like a walkback, somebody publishes the real number, somebody senior notices, and the number gets fixed. Here is what the record actually shows. The first bulletin was labelled automatic on its face. It said so. That label is not a disclaimer buried in a footnote, it is the category of the product. Fivolks then published the revision as Earthquake Information Number 2, which means the numbering system itself preserves the trail. Bulletin 1 said this. Bulletin 2 says that. Both are public. Both stay public. A cover-up does not leave a numbered revision history. A cover-up deletes Bulletin 1, and the direction of travel is the normal one. Automatic magnitudes for offshore events revise downward far more often than they revise upward, for exactly the saturation and location reasons we just walked through. If agencies were in the business of managing fear, the incentive would run the other way, and the corrections would climb. There is also a practical test you can apply to any claim of this shape, and it costs nothing. Ask what the alleged cover-up would have to accomplish. In this case, the alleged concealment would be hiding a magnitude 7 near the Talord Islands, which is offshore in deep water, far from any dense population centre, on a stretch of boundary that produces earthquakes of that size regularly. There would be nothing to gain by hiding it, because there would be nothing frightening about it that is not already public. Meanwhile, the thing that is genuinely alarming in this region, the segment of fault that has been quietly accumulating strain for more than 100 years, is published, discussed, and openly named in hazard assessments. The scary thing is the thing they are telling you about. That is almost always the pattern, and it is the pattern here. The genuine lesson here is more useful than the conspiracy, and it is this. Never build a conclusion on an automatic solution. Not a personal conclusion, not a public one. In the first 10 minutes after a significant earthquake, everything you are reading is a machine's best guess made from a fraction of the available information, published fast on the theory that a fast rough answer saves more people than a slow precise one. That is a good trade. It is not a good foundation for an argument. So the location correction changed where this earthquake was. The magnitude correction changed what it was, and that one moved by a factor almost nobody guesses correctly. Part 4. 11 times less. 7.0 to 6.3 is a difference of 7/10. Written down like that, it looks like a rounding error. It is not. The magnitude scale is logarithmic, and 7/10 of a magnitude unit corresponds to roughly 11 times less radiated seismic energy. 11 times. That is not an adjustment to a number. That is a different class of event. If the original estimate had held, we would be talking about an earthquake with 11 times the energy release, in a location 258 kilometers away, on a different piece of the plate boundary. Almost nothing about the story would be the same. It is worth slowing down on why the scale behaves this way, because almost every misunderstanding about earthquake size comes from here. Magnitude is not a measure of how much the ground shook at your feet. It is a measure of the total energy the rupture radiated, expressed on a logarithmic scale, which means each step up is a multiplication rather than an addition. One full magnitude unit is roughly 32 times more energy. 2 full units is roughly 1,000 times more, and because the scale is continuous, the same multiplication applies to fractions of a unit. 2/10 of a magnitude is about a factor of 2, half a unit is about a factor of 6. 7/10, which is what we're dealing with here, is about a factor of 11. So a headline that changes from 7.0 to 6.3 has, in physical terms, thrown away 90% of the earthquake. What is left is not a slightly smaller version of the same thing. It is a different event with a different footprint, a different shaking radius, and a different hazard profile. Consider what the two solutions actually described. Under the automatic solution, this was a magnitude 7 earthquake near the Talord Islands. That is out in the Channel, between Mindanao and the northern tip of Sulawesi, in a region where the Sangihe Arc and the Molucca Sea Collision Zone are doing their own complicated business. An event there would have been a separate rupture, on a separate structure, arguably unrelated to anything that happened in June. It would have been a new problem. Fresh headline, fresh hazard assessment, fresh set of coastlines to worry about. Under the reviewed solution, it is a magnitude 6.3 to 6.4 sitting directly inside the zone of deformation surrounding the June 8th rupture. Same seismogram, same handful of minutes, two completely different stories, and only one of them is true. And the true one is, in a specific way, the more unsettling of the two. A new magnitude 7 off the Talord Islands would have been a discrete event. Alarming, worth covering, and then over. What we actually have is evidence that the June 8th sequence is still running, still producing strong earthquakes, still capable of shaking towns at intensity 5, 2 months after the main shock. That is the reframing, and it is the first real conclusion of this video. Today is not a new earthquake story. Today is the June story, continuing, in a place along that boundary where it had not yet gone. Which raises the obvious question. If June 8th was 2 months ago, and if the crust down there has already produced thousands of aftershocks, why is it still doing this? Part of the answer is simply that this is what large earthquakes do. A magnitude 7.8 rupture does not release its stress and then hand back a tidy settled crust. It leaves a mess. It leaves a fault surface that slipped unevenly, patches that moved a lot next to patches that barely moved at all, and it redistributes stress onto everything around it. Sorting that out takes months. Sometimes it takes years. Think of it the way you would think of a long crack propagating through a pane of glass under load. The crack relieves the stress along its own length. It does not relieve the stress in the glass beside it. In fact, it concentrates it there, at the tips, at the edges, everywhere the crack stopped. The material around a rupture is left holding more than it was holding before, and it holds it until something gives. That is the process that has been running under southern Mindanao since the 8th of June, and thousands of small failures are what it sounds like from the surface. But the other part of the answer is the part that makes this worth your time, and it is a specific number in the moment tensor that has barely been mentioned anywhere in today's coverage. Before we get there, one more thing about the initial 7, because it is going to pay off later, and I do not want it to arrive from nowhere. When that automatic bulletin published a magnitude 7 at this general geometry, a tsunami evaluation was triggered. That was correct behaviour. It was not an overreaction, and it was not theatre. It happened because there is something particular about shallow thrust earthquakes near a trench axis that makes them dangerous out of all proportion to their size, and a magnitude 7 with that geometry sits right at the threshold where the calculation changes. At 6.4, it is not a practical concern. That is why the flag came down. At 7.4, with the same fault, the same depth, and the same mechanism, the conversation would be entirely different, and I will show you exactly why when we get to the depth. For reference, and to keep this grounded in what these things actually do to people, the June 8th earthquake did generate a tsunami. Waves of roughly 1 to 1.4 meters, 3.3 to 4.6 feet, were recorded across 6 coastal areas of Sultan Kudarat and Sarangani. I want to be careful about how that number lands because a 1 meter wave sounds survivable, and people consistently underestimate it. We will come back to that too, so here is where we stand at the end of the first act. We know where this earthquake was, we know how big it was, we know it belongs to the June sequence rather than standing on its own. We know that the first answer we got about it was wrong in both location and size, and we know precisely why. What we do not yet know is which fault moved, and that question, on this particular plate boundary, at this particular moment, 2 months into a sequence that has already killed more than 100 people, is not academic. There is a fault in this region that scientists have been watching with something close to dread. There is another one that nobody was especially worried about. Today, one of them moved. The moment tensor tells us which, and it is not the one you would expect. Part 5, 92%. Every earthquake leaves a fingerprint of how it broke, not a description of where, not a description of how big, a description of the geometry of the failure itself, of which way the rock was pushed and which way it moved and what kind of process was responsible. Seismologists call it the moment tensor, and if you have ever seen an earthquake report with a little sphere shaded black and white in a pattern that looks like a beach ball, that is what you are looking at. The moment tensor for today's earthquake is unusually clean, 92% double couple. That figure is the whole reason this event is worth analysing instead of just reporting, so let us take it apart. When you record seismic waves at stations all around an earthquake, the pattern of first motions carries information about the source. At some stations, the ground first moves up. At others, it first moves down. The distribution of ups and downs across the globe is not random. It maps directly onto the geometry of whatever happened at the source, and if you collect enough of those observations, you can solve for a mathematical object that describes the forces involved. That object breaks down into 3 components, and the proportions tell you what kind of event you are dealing with. The first component is the double couple. Picture 2 blocks of rock in contact along a plane, and picture one of them sliding relative to the other. That sliding requires a specific arrangement of forces, a pair of opposed force couples, which is where the name comes from. A double couple is the mathematical signature of ordinary faulting, rock slipping past rock. Nothing more exotic than that. The second component is the isotropic term. This is volume change. Something at the source got suddenly bigger or suddenly smaller. An explosion is the obvious example, because an explosion pushes outward in every direction at once, and the seismic waves it generates show first motion upward at every station regardless of azimuth. A cavity collapse is the mirror image, pulling inward everywhere. Either way, the isotropic term is large. The third component is the compensated linear vector dipole, which is a mouthful and gets abbreviated to CLVD. This one is the messy one. It appears when the source is more complicated than a single plane of slip. Fluid moving through cracks produces it. Magma forcing its way into a fracture produces it. Ruptures that jump between misaligned fault segments produce it. When a solution has a large CLVD component, it is telling you that something structurally complicated happened, and that you should be careful about drawing simple conclusions. Today's earthquake is 92% double couple. That means the isotropic and CLVD components together account for 8%, which is at or near the level of ordinary solution noise. There is no volume change to speak of. There is no fluid signature. There is no structural complexity to argue about. This was one block of rock sliding over another block of rock, along a single pre-existing plane, and then stopping. There is one honest complication in reading a double couple solution, and I would rather give it to you than pretend it does not exist because it becomes important shortly. A double couple solution always gives you 2 possible fault planes, not one. They are called the nodal planes, and from the seismic waves alone they are mathematically indistinguishable. The radiation pattern produced by slip on the first plane is identical to the radiation pattern produced by the appropriate slip on the second. The wave field genuinely cannot tell them apart. So how does anybody ever decide which plane was real? You use something other than the waves. You look at where the aftershocks cluster, because aftershocks tend to illuminate the surface that actually slipped. You look at the known geology, because if one plane happens to line up with a mapped structure and the other does not, that is informative. You look at the regional stress field, because faults fail in the orientations that regional stress favours, and in a subduction setting you look at whether one plane matches the known dip of the plate interface. That is the reasoning we are about to do, and it is why the two planes in today's solution, at roughly 80 and 96 degrees, are going to matter so much. Because one of them dips east, and there is precisely one structure in this region with that geometry. The rest of the solution fills in the details, and it is worth having them all on the table before we interpret them. The W phase solution puts the magnitude at 6.35 at a depth of 11.5 kilometers, which is 7.1 miles, and it gives a half duration of 3.5 seconds. Half duration is a measurement that does not get talked about much outside seismology, and it is a genuinely interesting number because it is the closest thing you get to a stopwatch on the rupture itself. Roughly speaking, it describes how long the fault was actually moving, not how long the shaking lasted at the surface, which is much longer and depends on where you're standing and what the local geology does to the waves. How long the rupture took to happen? 3.5 seconds. Sit with that for a second, because the ratio is remarkable. 3.5 seconds of slip on a fault plane a few kilometers across, and the consequence is a sequence of readjustments that has already been running for 2 months and will run for months more. That asymmetry between how long the failure takes and how long the recovery takes is the fundamental shape of every earthquake sequence on the planet. Now, the clean solution does something else useful, and I want to deal with it head-on, because whenever a strong earthquake hits a region that has already been shaken, a particular set of claims shows up within the hour. The claim is that something triggered this. Take your pick of mechanism. Solar activity because a coronal mass ejection happened to arrive within some window. Wastewater injection or drilling. Weapons testing. Some deliberate act, somewhere, by someone. I want to take the underlying question seriously first because it is not a stupid question. It is asking whether the energy that came out of the ground came from the ground or from somewhere else. That is a legitimate physical question, and it has a definitive answer, and the answer is sitting right there in the moment tensor. An explosion produces a large isotropic component. That is not a matter of opinion or interpretation. It is a matter of what the wave field looks like, and it is precisely how nuclear test monitoring works. The entire international monitoring system for detecting clandestine tests rests on the fact that explosions and earthquakes produce mathematically distinguishable seismic signatures, and the isotropic component is the primary discriminant. A buried explosion pushes outward in all directions. A fault does not. A fluid-driven or volcanic source produces a large CLVD component for the reasons we walked through. Injected fluid opens cracks, and opening a crack is not the same geometry as sliding along one. Today's solution has essentially neither. 92% double couple leaves 8% of room for everything that is not ordinary tectonic faulting, and 8% is inside the range you would expect from measurement uncertainty alone. There is simply nowhere in the mathematics to put a non-tectonic source, and then there is the context which points the same direction. This earthquake occurred inside an active aftershock sequence, in a region that has produced 17 earthquakes of magnitude 6.5 or greater in the past decade, on a plate boundary that is converging at roughly 7.3 centimeters a year, 2 months after a magnitude 7.8. The simplest available explanation is that a very active fault system produced another earthquake. When the simplest explanation also matches the physics exactly, that is usually the end of the inquiry. But knowing how it broke is not the same as knowing which fault broke. A double-couple solution describes the geometry of the slip. It gives you 2 possible planes, mathematically indistinguishable from the wave field alone, and it tells you the orientation of the forces that drove the failure. What it does not do, on its own, is hand you a name. For that, you need the direction of the squeeze. Part 6. The direction of the squeeze. There is one number in today's solution that does more work than all the others combined. 255 degrees. That is the azimuth of the compression axis, and if you only remember one figure from this entire video, that is the one that identifies the fault. Every focal mechanism comes with a set of principal axes. The most useful one for our purposes is conventionally called the p-axis, for pressure, and in plain language it is the direction the rock was being squeezed hardest at the moment it failed. Not the direction the rock moved, the direction it was being pushed. 255 degrees, measured clockwise from north, points roughly west-southwest, which means the axis of maximum compression runs east-northeast to west-southwest. Now ask what sits along that line. East of the epicenter is Mindanao. West of it, under the water, is the Celebes Sea, and the Celebes Sea floor is subducting eastward, beneath Mindanao. The seafloor on one side is being driven under the island on the other, and the direction of that convergence is east-northeast to west-southwest. The compression axis in today's earthquake points exactly along the direction that the plates are converging. That is not a loose correlation. That is the fault telling you what has been pushing on it. The convergence itself is oblique Sunda to Philippine sea motion, running at roughly 7.3 centimeters per year. That number deserves a moment, because it is easy to hear centimeters and think small. 7.3 centimeters a year is about 3 inches. It is roughly the rate a fingernail grows, and if you imagine a fingernail growing, you imagine something imperceptible, which is correct. That is exactly the point. Nobody standing on Mindanao can feel this. No instrument at human scale registers it as motion. It is a background condition, but run it forward. 7.3 centimeters a year is 73 centimeters a decade. It is 7.3 meters a century. And on a locked fault, where the two sides are stuck together rather than sliding smoothly, that motion does not disappear. It accumulates as elastic strain in the rock, the way a bent stick stores the energy you put into bending it. The plates keep moving at the far field. The fault surface does not. The difference goes into the rock as deformation, and it sits there until the fault fails and releases it in seconds. That is the engine underneath everything in this story, and we will need it again later when we start doing arithmetic on how much strain is currently sitting unreleased on a specific stretch of this boundary. The word oblique in that description is doing real work too, and it is worth unpacking, because it explains why this particular corner of the Philippines is as complicated as it is. Convergence is called oblique when the plates are not colliding head-on. Instead of one plate driving straight into the other at a right angle to the boundary, it comes in at a slant, and when that happens, the motion tends to partition. The component of motion that is perpendicular to the boundary gets taken up by thrust faulting on the interface, which is what stacks rock and builds mountains. The component that runs parallel to the boundary gets taken up by strike-slip faulting, usually on separate structures inland from the trench, which slides sideways. That partitioning is exactly why southern Mindanao has both kinds of fault. The thrust component lives on the trenches offshore. The sideways component lives on the big strike-slip systems inland. They are two expressions of one motion, split apart by geometry, and it means the two families of fault are not interchangeable when you are trying to explain a specific earthquake. Each one takes a specific share of the plate motion in a specific direction and produces a specific mechanism. Today's mechanism is the thrust family. That places it offshore, on the interface, not inland on the sliding structures. We are going to make that elimination explicit in a moment, because the inland structures are the famous ones and they are the ones people will name first. Before that, one more consequence of the 7.3 centimeters. The rate is not just an engine, it is a clock. If you know how fast a boundary converges, and you know when a given segment last released, you can calculate how much slip has gone unreleased in the interval. That calculation is the single most important piece of arithmetic in this entire story, and we will do it explicitly once we have established which segment we are talking about. The second thing the mechanism gives us is the geometry of the planes themselves. Both nodal planes in today's solution dip near 90 degrees. One is around 80, the other around 96. Now, when a solution gives you two planes at those angles, with the motion arranged the way it is arranged here, what you have is essentially pure dip-slip reverse motion. Dip-slip means the movement is up and down the slope of the fault rather than sideways along it. Reverse means the block above the fault moved up and over the block below it, which is what happens when rock is being compressed. That is a thrust earthquake. The textbook signature of a thrust earthquake in fact, without ambiguity or mixed components. It is also worth saying why reverse faulting is the mechanism that concerns people most on a subduction margin. Thrust faults are the ones that lift the seafloor. When the upper block rides up and over the lower one, and that happens underwater, the entire column of ocean sitting on top of the upper block gets lifted with it. That displaced water has to go somewhere, and where it goes is outward, in every direction, as a tsunami. Strike-slip earthquakes move ground sideways, which displaces very little water vertically, which is why enormous strike-slip events often produce almost no wave at all. Thrust earthquakes on subduction interfaces produce the tsunamis that kill tens of thousands of people. Today's earthquake was a thrust earthquake underwater, At 6.4, it lifted a small enough area by a small enough amount that the effect was negligible. The mechanism, though, is the tsunami generating mechanism. That distinction between the geometry being right and the size being wrong is going to come back with force. And the third thing is the strike. Both nodal planes strike north-northwest to south-southeast. Strike is the compass direction the fault line runs along the surface, and north-northwest to south-southeast in this exact segment is trench parallel. It runs the same way the trench runs. So now put the three findings side by side, because assembled they say something a single measurement could never say. The compression direction matches the plate convergence direction. The strike matches the trench. The motion is thrust, which is what convergence produces. Three independent measurements, all agreeing, all pointing at the same conclusion. This earthquake happened on the subduction system, not on some unrelated crustal fault that happens to be nearby, on the boundary itself, or on a structure directly attached to it, driven by the same plate convergence that built these islands in the first place, which narrows the field enormously. But there is one more piece of work to do before we can name a fault, because Mindanao has two other structures that everybody has heard of, and both of them are about to be eliminated. Part 7. The faults that didn't do this. Read anything about Philippine earthquakes for more than 5 minutes and you will run into two names, the Mindanao Fault and the Philippine Fault. The Philippine Fault in particular is one of the most famous structures in Southeast Asia. It runs for well over 1,000 kilometers, cutting diagonally through the archipelago, and it is the kind of feature that shows up on every regional tectonic map with a bold line and a label. Neither of them did this. Both are left lateral strike-slip systems. Strike-slip is the mechanism where two blocks slide horizontally past each other with no significant vertical stacking. The San Andreas is the example everybody knows. Stand on one side, look across, and if the fault moves, the ground on the far side shifts sideways relative to you. Left lateral simply specifies which way. The far side moves to your left. These are the structures that take up the sideways component of that oblique convergence we just described. They are the partition, running inland and roughly parallel to the general trend of the archipelago, absorbing the fraction of plate motion that the trenches cannot. They are also, for a general audience, the only Philippine faults with any name recognition at all, which means that whenever a significant earthquake happens anywhere in the country, they are the first structures reached for. It is a completely understandable reflex. When something happens in California, people say San Andreas, whether or not the San Andreas had anything to do with it. Both of these structures lie well to the north-northeast of today's epicenter, which is already an argument. But geography is the weaker half of the case, and I want to make the stronger half, because it is the kind of reasoning that lets you rule things out with confidence instead of just probability. A strike-slip fault cannot produce a thrust-focal mechanism. Not unlikely, cannot. The mechanism is the geometry of the slip, and horizontal sliding and vertical stacking are different geometries. They radiate different wave patterns. They give different first motions at different azimuths. If today's event had happened on a left lateral strike-slip fault, the solution would show near vertical planes with horizontal slip vectors and a compression axis oriented at roughly 45 degrees to the fault trace. That is not what came in. What came in is dip-slip reverse motion, with the compression axis aligned with plate convergence. The mathematics forbids the substitution. You cannot get one beach ball from the other geometry, and this is one of the genuinely satisfying things about seismology as a discipline. A great deal of earth science involves inference from incomplete evidence, arguing about interpretation, weighing one model against another. Focal mechanisms are not like that. The wave field either shows you thrust motion or it does not. There is no version of today's data that is compatible with a left lateral strike-slip source, and no amount of preference for a familiar name changes that. The elimination is clean, and it is final. So the two famous names are out, and that is not a trivial result, because ruling out the familiar structures is exactly how you get forced onto the unfamiliar one that actually matters. Most coverage of this event will reach for a name the audience recognizes. The correct answer is a structure most people have never heard of, and getting there requires eliminating the ones they have, which leaves the subduction system itself, and within it, exactly two candidates. The Sangihe Trench, running down toward Indonesia, where the descending slab dips west, and the Cotabato Trench, along the southwestern edge of Mindanao, where the descending slab dips east. Two trenches, opposite dip directions, one earthquake, with a solution that has to match one of them and cannot match both. And this is where the story turns because only one of those two candidates fits the depth. Part 8. What June 8th actually did. To understand what today's earthquake means, you have to understand what it is an aftershock of. At 37 minutes past 11 at night, Coordinated Universal Time, on June 7th, which was the early hours of June 8th in local time, a magnitude 7.8 earthquake struck offshore of Sarangani province and General Santos City in southern Mindanao. The first automated solution ran as high as 8.2. I want you to notice that, because we just spent a section on it. Automatic high, reviewed lower, the exact same pattern that produced today's magnitude 7 bulletin produced an 8.2 bulletin in June, and both were revised downward once human analysts and better data got involved. That is not a coincidence, and it is not carelessness. It is the systematic behavior of rapid magnitude estimation for large offshore events, and it repeats because the underlying physics of the measurement repeats. The reviewed magnitude settled at 7.8. The depth is where it gets interesting, and I need you to hold this number, because the entire back half of this video turns on it. Fivolks put the June 8th main shock at approximately 33 kilometers, about 21 miles. The USGS put it near 55 to 57 kilometers, 34 to 35 miles. Both of those are deep. Even taking the shallower of the two, 33 kilometers is well down the subduction ramp, a long way from the trench axis, in stiff rock under serious confining pressure. Remember the number, 33 at the shallow end, 57 at the deep end. The maximum intensity from the June event was 8, and where intensity 6 means objects falling off shelves, intensity 8 is a different world. At intensity 8, ordinary buildings sustain considerable damage. Walls separate from frames, chimneys and towers come down, heavy furniture overturns, structures that were not designed with seismic loading in mind, which describes an enormous fraction of the residential building stock in the affected area, start failing structurally rather than cosmetically. And then there was the water. Fivolks recorded tsunami waves of roughly 1 to 1.4 meters, 3.3 to 4.6 feet, across 6 coastal areas of Sultan Kudarat and Sarangani. I have to spend a minute on this because a 1-meter wave sounds survivable, and people consistently underestimate it, and that misunderstanding has killed a lot of people over the years. The thing about a tsunami is that it is not a wave in the sense that a beachgoer understands waves. A normal breaking wave is a rotating parcel of water, with a short wavelength. It hits you, it passes, and then the water goes back. A tsunami has a wavelength measured in kilometers, which means when it arrives it does not break over you and recede, it keeps coming. It is a wall of water with an entire ocean behind it, and it arrives as a surge that does not stop rising for minutes. At 1 meter, that surge will take an adult off their feet. Once you are off your feet, you are in a current moving at speeds a strong swimmer cannot fight, and you're not in clean water. You're in water carrying everything the wave picked up on its way in. Vehicles, timber, roofing, furniture, whatever the first 100 meters of coastline contained. People are killed by the debris field as often as by the water, crushed against structures or pinned underwater by something floating on top of them. And then the water goes back out, and the return flow is often worse than the arrival, because now it is carrying the wreckage seaward with people in it. Waves well below 1 meter have killed people. 1.5 meters is lethal to anyone caught in the open. That is what June 8th put on those 6 coastal areas, and it is the baseline against which any future event on this system has to be measured. The response in the hours afterward followed the pattern these events always follow. A tsunami warning went out. It covered the immediate coastline, and it extended outward across the region, far enough that an advisory reached United States territory in Guam and the Northern Marianas before being cancelled later that morning. Warnings for distant coastlines get issued on the initial magnitude and cancelled once the actual wave heights come in from the gauges, which is the same speed first, accuracy second logic we walked through earlier, applied to water instead of to seismograms. On the ground, the aftershock started immediately. Within the first day, Fivolks was counting them in the hundreds. Within the first 2 days, more than 1,000. Several of them were themselves earthquakes large enough to have made headlines on any ordinary week, including events at magnitude 6.5 and 2 at magnitude 6.0. The agency warned that the sequence could run for more than a month. That warning turned out to be conservative. We are now approaching 2 months, and the sequence is still producing strong earthquakes, which is why we're talking about today at all. Now here is the part that has stayed unresolved since June, and it is the reason today's clean solution matters far beyond today. Nobody definitively established which fault produced the June 8th earthquake. The attribution was genuinely open. It may have ruptured the northern Sangye Trench. It may have ruptured the southern Cotabato Trench. It may have been some combination of both, a rupture that began on one structure and propagated onto the other, which is a thing that happens more often than the textbooks used to suggest. That ambiguity is not a failure of anybody's analysis. It is a consequence of the situation. You have a deep rupture on an obliquely converging boundary in a region where two candidate trench systems meet at a complicated junction and present broadly similar orientations. From the main shock alone, with a rupture that large releasing energy over a large area over tens of seconds, teasing apart which surface actually slipped is extremely hard. It is worth understanding why size makes this harder rather than easier, because the intuition runs the other way. A bigger earthquake produces a bigger signal, so surely it should be easier to characterize. The problem is that a magnitude 7.8 is not a point source. It is a rupture front travelling across a fault surface, potentially for tens of kilometres, over tens of seconds, releasing energy the entire way. Different parts of that surface may have different orientations. The rupture may have started on one patch and jumped to another. The moment tensor you get back is a weighted average of everything that happened, and an average of two different geometries does not necessarily look like either of them. That is exactly the situation in which the CLVD component climbs and the double couple percentage falls, and that is exactly the situation that makes a definitive fault assignment hard. Today's earthquake has none of those problems, and that is precisely what makes it useful. We covered this story on the day it happened, in the video from June 8th on the magnitude 7.8, and at that point the honest answer was that the fault had not been identified. It still has not been formally identified. The question has been sitting open for 2 months, and it is not an academic question, which is the thing I want to make sure lands. Which structure ruptured in June determines which structure is now unloaded and which is now loaded. It determines where the stress went. It determines which neighbouring segments moved closer to failure and which moved further away. Every forward-looking statement anybody makes about hazard in southern Mindanao over the next several years depends on getting that answer right, and for 2 months the answer has been a shrug with 2 candidates in it. You cannot resolve it by staring harder at the June waveforms. Those have been analysed exhaustively already. What you need is a new independent piece of evidence produced by the same system, clean enough to interpret without ambiguity. That is what arrived today at 14 minutes past 12. And this is where today's earthquake stops being a news item and becomes a piece of evidence. Because today's rupture was small, shallow, simple, and 92% double couple, which makes it the cleanest signal this sequence has produced. Where the main shock was too big and too complex to resolve, today's event is unambiguous. It has exactly one geometry, and that geometry has a direction. Today's solution is east dipping. The Sangye side dips west. That single fact does more work than anything else in this story, and it points at the other candidate. Part 9. The number nobody reported. Today, 11.5 kilometres. June 8th, 33 kilometres by FIVOLX, 55 to 57 by the USGS. That is the finding. That is the thing in today's moment tensor that I have not seen reported anywhere, and it changes the interpretation of this entire sequence. 11.5 kilometres is 7.1 miles. 33 kilometres is about 21 miles. 57 kilometres is about 35 miles. Even taking the shallowest available estimate for June, today's earthquake happened roughly 22 kilometres higher in the crust than the main shock did. Taking the deeper estimate, it happened 45 kilometres higher, which means today's earthquake is far up dip of the patch that broke in June. This is not a re-rupture of the same fault surface. Let me make sure that lands, because it is the difference between 2 very different stories, and almost every piece of coverage today has assumed the wrong one. The assumption most people made this morning was straightforward. Big earthquake in June, strong earthquake in the same region in August, therefore the same fault has moved again, therefore whatever broke in June did not finish breaking. That is a reasonable assumption, and it happens to be wrong, and the reason it is wrong is the depth. Go back to the ramp. The subduction interface descends from the trench inland. Near the trench it is shallow, only a few kilometres below the seafloor. Move landward along it and it deepens steadily. So the depth of an earthquake on that interface tells you, quite precisely, how far along the ramp it happened. An earthquake at 33 to 57 kilometers depth is well down the ramp, inland of the trench, under considerable overburden, in stiff rock at high confining pressure. That is where the June 8th rupture lived. An earthquake at 11.5 kilometers is way up near the top of the ramp, close to the trench axis, in the shallowest part of the system, in material that is a completely different beast mechanically. Those are not the same place on the fault. They are not even close, and a fault surface does not re-break in a spot 40 kilometers away from where it broke before and call that the same rupture. What we are looking at is a different part of the same system. There are exactly two candidate structures that fit, and both of them are worth understanding. The first is the shallow near-trench portion of the subduction interface itself, the very top of the ramp where the descending plate has just begun to bend downward, and the contact between the two plates is at its shallowest. This part of the interface has a reputation. For decades it was thought to be largely aseismic, meaning it was assumed to slide steadily rather than store up strain and release it in earthquakes, because the material there is soft, wet, and poorly consolidated. Then Tohoku happened in 2011, and the shallow near-trench portion of that interface slipped by an amount that shocked the entire field, and that assumption did not survive. The second candidate is a splay thrust in the accretionary wedge, and this one needs a bit of building because it is not a structure most people have a picture for. When one plate subducts beneath another, the sediment sitting on top of the descending plate does not all go down with it. A great deal of it gets scraped off, the way snow gets scraped off a driveway by a plough, and it piles up against the leading edge of the overriding plate. Over millions of years, that scraped-off material stacks into an enormous wedge-shaped pile, kilometers thick, sitting on top of the plate interface. That is the accretionary wedge. The wedge is not a passive heap. It deforms internally. It gets shortened and thickened as more material arrives, and to accommodate that shortening it develops its own faults, which are thrusts, and which typically branch upward off the main plate interface toward the seafloor. Those branching faults are called splay faults, and they are structurally above the interface riding on top of it. Both candidates put today's earthquake in the shallow part of the system, near the trench, above the June rupture patch, on a structure loaded up by what June did, and here is where today's east-dipping solution finally pays off. The Sangihei side dips west. Today's solution dips east. That argues for the Kotabato Trench as the culprit for today's event, and for the aftershocks that have been running with it. Now, I want to be careful about how strong a claim I make here, because the honest version is more interesting than the overclaimed one. This does not settle the June attribution by itself. A single aftershock mechanism is one line of evidence, not a formal reassignment, and formal reassignments go through analysis and review, and eventually literature. What it does is put a substantial thumb on the scale. If the aftershock sequence surrounding a rupture is producing east-dipping thrust mechanisms consistent with one candidate structure and inconsistent with the other, that is the kind of evidence that resolves attribution questions. It just resolves them in the fullness of time rather than in a bulletin. So why did this particular patch of fault fail today, 2 months after the main shock? The mechanism has a name, and it is the most useful concept in this entire video: static Coulomb stress transfer. Here is how it works, step by step. Before an earthquake, a fault is loaded. The rock on either side is being pushed by plate motion, the fault is stuck, and elastic strain accumulates in the surrounding material. When the fault finally slips, it releases that strain along the patch that moved. On that patch, stress goes down. That part is intuitive. What is less intuitive is what happens everywhere else. The rock surrounding the slipped patch has to accommodate the fact that its neighbour just moved. It gets pulled and pushed into a new configuration, and in specific regions around the rupture, the stress does not go down. It goes up. Those regions have a predictable geometry. They sit at the along strike ends of the rupture, beyond where the slip stopped, and they sit up dip and down dip of the slipped patch, above it and below it on the ramp. The magnitudes involved are small in absolute terms. Coulomb modelling of large earthquakes typically finds stress increases in these lobes on the order of a few tenths of a bar to a few bar. For scale, a bar is roughly atmospheric pressure at sea level. Against the tens or hundreds of bars of stress drop in the rupture itself, and against the enormous confining pressures at depth, that is a rounding error. But it is not a rounding error if the fault it lands on is already almost ready to fail. A fault that has been accumulating strain for decades or centuries sits very close to its failure threshold. Adding a fraction of a bar to something that is a fraction of a bar away from breaking is enough. It does not create the earthquake. It advances the clock on one that was coming anyway. Today's event sits up-dip of the June rupture on a thrust mechanism aligned with regional convergence in exactly the geometric position where Coulomb modelling would predict a stress increase. It is a textbook expression of the process, and this is where the word aftershock becomes technically correct and practically misleading at the same time, which is the most important sentence in this video. Technically, today's earthquake is an aftershock. It followed a main shock. It occurred within the aftershock zone. It was triggered by stress changes from that main shock, and Fivolks is characterizing it as one. All of that is accurate, but the word aftershock carries a connotation that does not apply here. When most people hear aftershock, they hear settling. They picture a fault that broke and is now rattling itself into a comfortable position and will shortly be quiet. Aftershock sounds like an ending. What we actually have is a different structure, up-dip of the one that broke, failing because June 8th loaded it. That is not settling. That is propagation. Stress transfer onto adjacent structures is precisely the mechanism by which large earthquakes walk along a plate boundary over months and years and decades. It is what happened along the North Anatolian Fault through the 20th century, where a sequence of major earthquakes marched progressively westward across Turkey over roughly 60 years, each one loading the next segment. It is not the mechanism by which a sequence winds down. It is the mechanism by which a sequence continues. Which brings us to the thing I promised you back in the first act about why the initial magnitude 7 triggered a tsunami evaluation. Shallow thrust earthquakes close to the trench axis are disproportionately tsunami-genic. That is one of my favourite words in this entire field, and I'm glad I get to say it to you. Tsunami-genic. Tsunami-generating. They punch above their weight, and there are several reasons why, and they compound. First, geometry. The closer to the trench a thrust ruptures, the more of its motion is directed vertically at the seafloor rather than being absorbed by the overlying rock column. A deep rupture lifts a broad, smeared-out area by a small amount. A shallow rupture lifts a smaller area by a lot, and sharp seafloor displacement is far more efficient at generating waves. Second, the water depth. Near the trench, the ocean is deep, and the deeper the water column that gets displaced, the more energy goes into the wave. Third, and this is the subtle one, the material properties. The rock at the shallow end of a subduction interface is soft. It has low rigidity, and for a given amount of seismic moment, low rigidity material has to slip further to produce it. So a shallow near-trench earthquake can produce dramatically more physical displacement of the seafloor than its magnitude would suggest. These events also tend to rupture slowly, radiating less high-frequency energy, which means the shaking they produce feels weaker than the wave they generate. There is a whole category of these things called tsunami earthquakes that have killed thousands of people who did not evacuate because the ground motion felt survivable. At magnitude 6.3 or 6.4, none of this is a practical concern. The displacement is too small. That is why the flag came down. At magnitude 7.4, on the same fault, at the same depth, with the same mechanism, it is an entirely different conversation. And that is precisely why an automated system that thought it was looking at a magnitude 7 near this geometry triggered a tsunami evaluation within 12 minutes. The system was not being alarmist. It was correctly recognizing a fault geometry that punches above its weight and reacting to the size it had been handed. So today's earthquake was loaded by June, on a structure June did not break, in the shallowest and most tsunami-efficient part of the system. Which raises the question we have been circling this entire time. If June loaded this, what else did June load? Part 10. The buildings that never got fixed. The Fivolks bulletin says no damage is expected. That is a reasonable statement. It is also a statement with an assumption buried inside it, and I want to pull that assumption out into the light, because it is the difference between what the bulletin describes and what is actually going to happen in those towns. Damage estimates are calibrated against structurally sound buildings. That is how the models work, and it has to be how they work. You cannot generate a rapid impact estimate without assuming something about the building stock, and what you assume is a distribution of construction types in normal condition. So many % reinforced concrete, so many % confined masonry, so many % unreinforced, each with a known fragility curve describing how it behaves at a given level of shaking. Nothing in that framework has a variable for buildings that were already damaged 8 weeks ago. and in southern Mindanao right now, that is the entire situation. As of July 21st, the June 8th earthquake had damaged or destroyed more than 121,300 homes. 121,000. That number does not describe a disaster zone with a hard edge around it. It describes a condition spread across the whole affected region. Some of those structures came down entirely. Many more are still standing, still occupied and carrying damage. Cracked walls, separated joints, mortar that debonded, columns with hairline fractures running through them that nobody has assessed and nobody has repaired, because in a region where 121,000 homes need attention, structural assessment for a house that is still standing is a long way down the list. The human toll, as of that same July 21st count, was at least 106 dead, 1,316 injured, and 7 still missing. I want to flag something about those figures, because you will see very different numbers if you go back and read the coverage from the days immediately after June 8th. In that first window, the reported toll ran between 32 and 45 dead, with injury counts anywhere from 200 to 630. Those were not wrong. They were first-day numbers, compiled inside 24 hours, from areas where roads were blocked and communications were down, and nobody had reached the worst affected barangays yet. The toll from a major earthquake almost always climbs for weeks, as landslide sites get excavated, as remote communities get reached, as people in hospitals do not survive their injuries. 106 is the accumulated official count as of the 21st of July, and it may well not be final. And there is a second layer underneath the housing figure that the numbers do not show you directly. When 121,000 homes are damaged or destroyed, the people who lived in them go somewhere. Some go to evacuation centres, many more go to relatives, to neighbours, into structures that were not built to hold 2 households. Others go back into their own damaged houses, because 8 weeks is a long time to live in a gymnasium and because the alternative is nothing. That last group is the one that matters here. They are sleeping inside the exact structures whose capacity June reduced, and they were sleeping in them today. The 7 still missing carry their own weight in this. Missing, 8 weeks on, in a landslide-prone region, usually means buried. It means a site that has not been fully excavated, either because the terrain is unstable or because the resources went to the living. Every one of those 7 is a family that has not been able to stop, and a piece of ground that is still being worked. Now put today on top of that, Glan reported intensity 5, strong shaking. In a town in Sarangani province that experienced intensity 8 in June, that lost people, and whose masonry is already carrying damage. The physics of what that does is worth walking through, because cumulative damage is not intuitive. Masonry does not fail the way a metal beam fails. A steel member bends, and if you unload it before it yields, it springs back to where it was. Masonry is brittle, and it is assembled from units held together by mortar, and when it is overstressed it cracks. Cracks do not heal. Mortar that has debonded from a brick does not rebond when the shaking stops. What you are left with is a wall that has the same shape it had before, and substantially less capacity than it had before. Worse, the cracks concentrate stress. A wall with a crack running through it is no longer distributing load evenly across its section. The load routes around the crack, which means the intact material next to the crack is carrying more than its share, which means the crack propagates further under the next event than the size of that event would suggest. So a wall that survived June at, say, 80% of its original capacity does not meet today's shaking with the strength it was built with. It meets it with what June left, and the next event after this one meets it with what today leaves. That progression is why earthquake sequences kill people in buildings that survived the main shock. It is not that the aftershocks are stronger, it is that the buildings are weaker. It is also why the most dangerous moment in a sequence is often not the main shock at all. After the main shock, people are outside. They are alert, they are in the street, they are sleeping in the open because they do not trust the walls. Then weeks pass. The shaking becomes routine. Confidence returns because confidence always returns, because you cannot sustain fear indefinitely and still function. People move back indoors, into the buildings that the main shock weakened, and that is the moment at which a moderate aftershock becomes lethal. This is not hypothetical. It is one of the most consistent patterns in earthquake casualty data worldwide, and it is the reason agencies keep issuing aftershock advisories long after the public has stopped reading them. The building stock in this part of Mindanao makes it more acute. A great deal of residential construction across the affected provinces is concrete hollow block, often unreinforced or lightly reinforced, sometimes built incrementally over years as money allowed. That construction type performs poorly under lateral loading even when it is intact, because hollow block has very little tensile strength, and the mortar joints are the weak plane. Shake it once hard enough to open the joints, and its remaining capacity drops sharply. It does not announce that it has dropped. It looks the same from the street. None of which is a prediction that Glan is going to see collapses. The honest position is that Fivolks is probably right, and no significant damage will be reported. A magnitude 6.4 at that distance is not, in the ordinary case, a structure-destroying event. The honest position is also that the models cannot see the thing that makes this case unusual, and that a magnitude 6.4 into pre-damaged masonry is genuinely not the same event as a magnitude 6.4 into intact masonry, which means the reports over the next 24 to 48 hours are worth actually watching rather than assuming. And this connects back to the thing we've been building toward this entire video, because the vulnerability question and the central question turn out to point at the same stretch of coastline. The question of what today's earthquake does to people is about the towns along the southern Mindanao coast and the condition of what they are living in. The question of where this sequence is going is about which segment of the Cotabato Trench fails next. Those are different questions with different methods and different timescales. They resolve onto the same map, the same coastline, the same towns, which is why the next thing we need to look at is not what today's earthquake did, but how it fits into the 8,500 earthquakes that came before it. Part 11. 8,500. By June 19th, 11 days after the main shock, Fivolks had recorded more than 8,500 aftershocks. 8,500 in 11 days. That is more than 700 a day, more than 30 an hour, sustained for a week and a half. Most of them were far too small to be felt by anyone. Some of them were not. 3 exceeded magnitude 6.0, and the largest of the entire sequence so far came in at approximately 6.5. There are 2 ways to react to a number like 8,500, and only one of them is correct. The wrong reaction is that this is extraordinary, and something unprecedented is happening. The right reaction is that this is precisely what a magnitude 7.8 does in a well-instrumented region, and the count is that high partly because the instruments are good enough to catch events nobody feels. We have 2 statistical frameworks for this, and both of them are worth having, because they are what turn a scary number into a diagnostic tool. The first is Both's law. Both's law is an empirical observation, and it is disarmingly simple. The largest aftershock in a sequence tends to be about 1.1 to 1.2 magnitude units smaller than the main shock. Not always. It is a statistical regularity, not a rule of physics, but it holds well enough across enough sequences worldwide that it is the first thing you check. Run it for June 8th. A magnitude 7.8 main shock minus 1.1 to 1.2 predicts a largest aftershock somewhere around 6.6 to 6.7. The observed largest is approximately 6.5, which sits just inside expectation, slightly on the low side. Nothing anomalous. The sequence is producing what a sequence of this size produces. It is worth pausing on why Both's law works at all, because it is genuinely strange that it should. There is no obvious physical reason why the largest aftershock should scale to the main shock in a fixed way. The leading explanation is that an aftershock sequence is essentially its own earthquake population, obeying the same size-frequency distribution that all earthquake populations obey, with a total energy budget set by the size of the stress redistribution the main shock produced. Feed a bigger budget in, and the largest event that population produces scales up with it. The 1.1 to 1.2 offset falls out of the arithmetic rather than being imposed on it. What that means practically is that Both's law is a check on whether a sequence is behaving like a sequence. If the largest aftershock came in far above expectation, that would suggest the main shock had been underestimated, or that a separate structure had been triggered rather than a normal aftershock population. 6.5 against an expected 6.6 to 6.7 raises none of those flags. The second framework is Omori's law, and this one is the more useful of the 2 for our purposes. Omori's law describes how aftershock rate decays with time. Roughly, the rate falls off as the inverse of the time elapsed since the main shock, which means the first day produces enormously more aftershocks than the second more than the third, and so on, with the curve flattening as it descends. Run that forward and you get the shape of a normal sequence. Hundreds per day in the first week, dozens per day in the first month, a handful per day by the second or third month, with occasional larger events punctuating the decline, and a tail that runs at a rate slightly above the regional background for years, which means that today's earthquake, arriving in the 8th week, is entirely consistent with a normal decay curve. Occasional strong events late in a sequence are expected. Their arrival is not a signal. We built this same framework out in detail in the video from the middle of July on the Mexico aftershocks, when a burst of activity along the Middle America Trench raised exactly the same question in a completely different ocean. The lesson there is the lesson here, and it is worth saying plainly. In an aftershock sequence, individual events are noise. The shape of the sequence is signal. You do not learn anything from one earthquake. You learn from whether the population of earthquakes is doing what the population of earthquakes is supposed to do. The spatial footprint is worth having too, because it explains why events that seem far apart still belong together. The initial aftershock zone for the June 8th rupture covered roughly 165 by 150 kilometers, about 103 by 93 miles extending south of General Santos City. That is an area of something like 25,000 square kilometers, larger than the state of New Jersey, larger than Wales. That footprint is the reason today's event, which happened 100 kilometers south of where June's destruction was concentrated, is still inside the sequence. It is a big sequence. It always was. Other recent events in the same zone have been characterized the same way. There was a magnitude 6.5 offshore Davao Occidental. There was a magnitude 5.1 near Balut Island on August 1st, 4 days before today's event, in essentially the same neighborhood as today's epicenter. That last one deserves a note. A magnitude 5.1 on August 1st and a magnitude 6.3 to 6.4 on August 5th, in the same area. In a sequence this active, 4 days apart in the same neighborhood does not automatically mean anything. But it is the kind of pattern that becomes meaningful in hindsight, and it is the kind of pattern that only becomes visible if somebody is tracking the map rather than the headlines. And that word, hindsight, is doing a lot of work because it is the permanent limitation of this entire field. A foreshock is not a category of earthquake. It is a label applied retrospectively. There is no measurement you can make on an earthquake as it happens that tells you whether something larger is coming behind it. The August 1st magnitude 5.1 is called an aftershock today. If a magnitude 7 follows in the same place next month, the same event will be relabeled a foreshock in every paper written about it, and nothing about the seismogram will have changed. Only the thing that came after. The base rate is small. Across global catalogues, something on the order of 5 or 6% of moderate earthquakes turn out to be followed by something larger within a few days, which means that 19 times out of 20, the answer is no. It also means that 1 time out of 20 it is not, and there is no way to know in advance which one you are in. That is the uncomfortable center of earthquake science, and no amount of instrumentation has moved it. We can tell you with extraordinary precision what just happened. We cannot tell you what happens next. So here is where the statistics leave us. Large aftershocks above magnitude 6 are entirely normal after a 7.8. 8,500 events in 11 days is normal. A 6.5 as the largest is normal. A 6.4 in the 8th week is normal. Today's earthquake is, statistically, unremarkable. But normal is not the same as finished, and this is the hinge the whole video turns on. Everything in this section describes a sequence behaving exactly as it should, in the place it is supposed to behave. The aftershocks are decaying, the magnitudes are within expectation. The footprint is the footprint that was established in June, which is precisely why the place where nothing is happening matters more than any of it. Because there is a stretch of this same fault system, not far north of everything we have been discussing, that has not produced any of these earthquakes. Not one of the 8,500, not the 6.5, not today's. It has been silent since 1918. Part 12. The stretch that hasn't moved. Since 1918. Everything up to this point has been about the earthquake that happened. The rest of this is about the one that has not. In the weeks after June 8th, as analysts worked through the rupture and mapped where the slip had gone and where it had stopped, something showed up that has been quietly shaping every hazard conversation about this region since. There is a section of the Cotabato Trench, roughly 70 to 100 kilometers long, about 43 to 62 miles, that has not ruptured since at least the 1950s, and probably not since 1918. 1918 is the more likely date, and the reason it is the more likely date is what makes this uncomfortable. In 1918, this system produced a magnitude 8.3. I want to be careful with that number because it is not a model output and it is not a projection. It is a historical event. It happened. A magnitude 8.3 is not a hypothetical maximum derived from fault dimensions and assumed slip rates. It is the demonstrated capability of this structure, written into the record by the structure itself. For scale, an 8.3 releases something on the order of 45 times more energy than the 7.8 that struck in June. June killed at least 106 people and damaged 121,000 homes. So we have a segment of fault, 70 to 100 kilometers long, that last released more than a century ago on a system capable of a magnitude 8.3. And the geometry of where that segment sits is what makes it genuinely difficult to look away from. It sits between the June 2026 rupture on one side and the rupture area of a magnitude 7.5 from 2023 on the other. Picture that on a map. Draw the trench as a line. At one end of a stretch, mark the patch that broke in 2023 at magnitude 7.5. At the other end, mark the patch that broke in June of this year at magnitude 7.8. Between them, 70 to 100 kilometers of plate boundary that has done nothing. 2 major earthquakes, one at each end, and a quiet space in the middle. And this system has a second historical entry that belongs in this conversation because it is the one that tells you what these events do when they arrive at the wrong place at the wrong time. In 1976, the Morro Gulf earthquake struck this same broad system at magnitude 7.9. What killed people was not primarily the shaking, it was the tsunami that followed it, which ran up along something on the order of 700 kilometers of coastline into communities that were asleep, in an era with no warning infrastructure worth the name. The death toll has never been established precisely. Estimates run somewhere between 5,000 and 8,000, 5 to 8,000 people from a magnitude 7.9 on this system within living memory. That is the context in which a seismologist looks at a 70 to 100 kilometer segment with an 8.3 in its history and no release since 1918. It is not an abstract hazard. There is a demonstrated worst case, and it is documented, and it happened to the same coastline. Now, if you have been watching this channel for a while, that shape should feel familiar, because we drew almost exactly the same picture yesterday in the video on the Kural Arc, where a burst of earthquakes organized itself into 2 clusters that bracketed the section of interface the 2025 magnitude 8.8 did not rupture, with a quiet center between them. Different ocean, different plate, different scale entirely, same geometric signature. When a plate boundary produces activity on both sides of a silent stretch, the silent stretch is the thing worth looking at. Here is the arithmetic that makes it more than a shape. The convergence rate across this boundary is roughly 7.3 centimeters per year. If a segment is locked, meaning the 2 sides are stuck together and not sliding, then the plates keep converging at that rate while the fault surface itself does not move. The difference accumulates as slip deficit. 7.3 centimeters a year is 73 centimeters a decade. 1918 to 2026 is 108 years. Run it. 108 years at 7.3 centimeters a year is roughly 7.9 meters of accumulated slip deficit. Nearly 8 meters, 26 feet. Now, I need to caveat that immediately, because a number that clean is always doing some hiding. That calculation assumes the segment is fully locked, and real faults are rarely fully locked across their entire surface. Some portion may be creeping, sliding steadily and releasing strain without earthquakes. Some portion of the convergence may be taken up on other structures nearby. The oblique geometry means not all of the 7.3 centimeters goes into thrust motion on this interface in the first place. Any serious estimate would use geodetic measurements of actual surface deformation to figure out the coupling ratio rather than assuming 100%. The way that gets measured properly when somebody does the work is with satellite geodesy. You put permanent receivers on the ground on the overriding plate, and you watch how they move over years. If the fault beneath them was sliding freely, those stations would sit still relative to the stable interior of the plate, because the motion would be absorbed at the boundary. If the fault is locked, the stations get dragged. They compress toward the trench, elastically, storing the deformation in the rock, and you can measure that compression in millimeters per year with enough precision to invert for how much of the interface is stuck and how much is sliding. That measurement produces a coupling ratio, and coupling ratios vary enormously between subduction zones and between segments of the same subduction zone. Some interfaces are almost fully locked and produce enormous earthquakes. Others are nearly fully creeping and produce very few. Many are patchy, with locked asperities surrounded by creeping regions, which is why ruptures often stop where they do. So the real deficit is probably meaningfully less than 8 meters. It is still measured in meters, and that is the point, because meters of slip deficit on a fault segment 70 to 100 kilometers long is, in earthquake terms, a large earthquake waiting to be assembled. Now let me be honest about the limits of this framework, because the seismic gap concept has a complicated history, and I am not going to sell it to you as more than it is. A seismic gap is a hypothesis, not a clock. The idea is straightforward. If a plate boundary is converging steadily, and most of it has ruptured recently, the stretch that has not ruptured must be storing strain, and is therefore more likely to fail than its neighbours. That reasoning is physically sound as far as it goes. The trouble is what happened when people tried to use it predictively. Gaps have been identified and then failed to produce the expected earthquake for decades. Earthquakes have occurred in places where no gap was identified, sometimes in places that had ruptured recently, and were therefore assumed to be safe. The famous Parkfield experiment in California, built on the premise that a segment with regular repeating earthquakes would produce the next one on schedule, ran more than a decade past its predicted window. Formal statistical tests of gap-based forecasting in the 1990s found it performed no better than assuming earthquakes occur randomly in space. So the concept survives as a hazard framing rather than a prediction tool. It tells you where the stakes are, it does not tell you when. There is a version of the gap idea that has held up better though, and it is the version that applies here. Rather than treating a gap as a countdown, treat it as a statement about what a future rupture could be. A segment 70 to 100 kilometers long, with meters of accumulated deficit, tells you the plausible size of the earthquake that segment can produce whenever it does produce one. That is a statement about magnitude, not about timing, and it is a statement you can actually defend. It is also the statement that matters for anybody designing a building or planning an evacuation route, because those decisions are about what to be ready for, not about what date to be ready by. And on that framing, the 1918 magnitude 8.3 is not a scary anecdote, it is the calibration. Which brings us to the version of this story that circulates every time a gap gets discussed publicly, and I want to address it directly because it comes up constantly. The claim is that scientists know something is coming and are not saying so, that there is information being held back, because telling people would cause panic, or hurt property values, or trigger a response nobody wants to pay for. Look at what is actually on the public record. The gap is published. Its length is published, 70 to 100 kilometers. Its bounding ruptures are published, the 2023 7.5 and the 2026 7.8. The 1918 magnitude 8.3 is in the historical catalogue and has been for a century. The convergence rate is published. The hazard concern is stated openly in assessments that anybody can read. The alarming thing is the thing they are telling you about. That is not what concealment looks like. Concealment looks like the frightening information being absent from the record and surfacing later. Here, the frightening information is the record. What is missing is not the hazard. What is missing is a date, and the reason a date is missing is that nobody on Earth has one. And I think that is actually harder to sit with than a conspiracy would be, which may be part of why conspiracies are attractive. A conspiracy implies somebody knows. It implies the information exists and is being withheld, which means there is a version of the world where you could get it. The real situation is that earthquake prediction remains impossible, not difficult, not restricted, not classified. There is no method anywhere in any country that reliably tells you when a specific fault will fail. Foreshocks are identifiable only in hindsight. Precursor signals have been chased for a century and none has survived rigorous testing. That segment could release next decade or next century, and the honest answer from the best instrumented, best funded seismological institutions on the planet is that they do not know and cannot know. Nobody is hiding the date. There is no date. Now here is the fact this entire section has been building toward, and it is a geographic one. The gap is to the north. Today's earthquake was at the southern end of the aftershock zone. Today's earthquake on the shallow near trench portion of the system, up dip of the June rupture, 37 kilometers southwest of Balut Island in the island municipality, was roughly as far from that unruptured segment as you can get, and still be inside the sequence. So this was not the scenario seismologists are watching for. Today did not touch the loaded segment, it did not relieve it, it did not rupture into it, it did not even happen near it. The loaded one is still sitting there. Which leaves one question about today's earthquake that almost nobody has asked properly, and the answer to it is worse than most people would guess. How much of the problem did today actually solve? Part 13. 1/150th. Today's earthquake released roughly 1/150th of the energy of the June 8th main shock. 1/150th. That is the answer, and it is worth sitting inside it for a moment, because it collides head-on with the intuition almost everyone has about earthquakes. The intuition goes like this: stress builds up. An earthquake releases it. Therefore any earthquake releases some of it, and a magnitude 6.4, which is a substantial earthquake by any normal standard, must have released a meaningful amount. The arithmetic says otherwise, and the arithmetic is not close. We touched on the logarithmic scale earlier, but now we need to run it properly, because this is where it does its real work. Each whole magnitude unit corresponds to roughly 32 times more energy. Not 32%, 32 times. So a magnitude 6 releases about 32 times what a magnitude 5 releases. A magnitude 7 releases about 32 times what a 6 releases, which is about 1,000 times a 5. Now walk from 6.4 up to 7.8. That is 1.4 magnitude units. One unit gets you a factor of 32. The remaining 4/10 gets you roughly another factor of 4.5. Multiply them together, and you land at something around 150, which is exactly the number we started with. Today's event released about 1/150th of what June 8th released. Turn that around and it becomes stark. You would need approximately 150 earthquakes of today's size, all of them on the same segment, to add up to the energy that came out of the ground on June 8th. And June 8th was itself only a fraction of what the unruptured segment is holding, because June 8th was a 7.8, and the 1918 event on this system was an 8.3, and that half unit is another factor of 5 or 6. There is a cleaner way to feel the same thing, which is to work in the other direction. Ask what it would take in terms of today's earthquakes to relieve the segment we have been discussing. Suppose that segment holds even a conservative 3 meters of slip deficit across 70 to 100 kilometers of fault. To release that seismically, you need earthquakes. Today's magnitude 6.4 ruptured a patch of fault a few kilometers across and slipped it by something on the order of tens of centimeters at most in one small place on a different structure. To cover the area involved, at the slip involved, you're not talking about 150 of today's earthquakes. You're talking about a number so large that the sequence would have to run for centuries at rates far above anything ever recorded. That is not how the energy gets out. It never has been. Plate boundaries do not release accumulated strain in a steady drizzle of moderate earthquakes. They hold it, and then release most of it at once. Every attempt to find a boundary that behaves the other way has found instead that the drizzle is a tiny fraction of the total, and the large events do the actual work. Now put it against the strain budget. A segment accumulating slip deficit since 1918 holds meters of it. Even discounting heavily for partial coupling and for motion taken up elsewhere, meters. A magnitude 6.4 does not consume meters of slip deficit. It consumes centimeters over a small patch in a place that is not even the segment in question. Today, relieved almost nothing, and it is worth extending that accounting to the whole sequence, because people make the same error at sequence scale that they make at event scale. There have been more than 8,500 aftershocks, 3 above magnitude 6. Surely all of that together adds up to something. It does not, and again the logarithm is y. In any earthquake population, the largest few events dominate the total energy release so completely that everything else is a rounding error. Thousands of magnitude 2 and 3 events sum to less than a single magnitude 5. The entire aftershock sequence, all 8,500 of them, release some small fraction of what the main shock released, and the main shock released some fraction of what the boundary has stored. The stress is not being drained by this. The stress is being redistributed by this, which is a completely different verb, and which is the reason today's earthquake happened at all. Now, I want to run a calibration check against all of this, because a section like the one you just heard can tip into alarmism very easily, and the numbers themselves do not support alarmism. This region has produced 17 earthquakes of magnitude 6.5 or larger in the past decade alone. 7 of those were above magnitude 7.0, 7 magnitude 7s in 10 years, in one region. Go back further and Fivolx counts at least 7 significant earthquakes between magnitude 5.7 and 8.0, affecting Sarangani and nearby provinces between 1917 and 2023. The last damaging event before June 8th was a magnitude 6.8 in 2023. Stop and consider what that means for the people living there. 7 earthquakes above magnitude 7 in 10 years is not a hazard that arrives occasionally and then recedes. It is a background condition of life. It means most adults in these provinces have personally experienced multiple major earthquakes. It means the building stock has been shaken repeatedly, in some cases repaired, in many cases not. It means the emergency response systems are experienced, which helps, and also that they are chronically stretched, which does not. It also means something about the interpretation of any single event, including today's. In a region producing this many large earthquakes, the base rate for a magnitude 6.4 is high enough that its occurrence on its own carries almost no information. What carries information is the detail, the depth, the mechanism, the position relative to a known gap. Which is exactly why this video has spent 2 hours on a moment tensor rather than on a magnitude. What that baseline tells you is that today is not unusual. Not in this region. A magnitude 6.4 off southern Mindanao is Wednesday. It is a significant earthquake that deserves attention, and it is also completely within the ordinary behavior of one of the most seismically active plate boundaries on the planet. That context is not a reassurance, and it is not a dismissal. It is a discipline. Because it is the thing that keeps the still-loaded framing honest. If I told you that today's earthquake was extraordinary, and that the region is behaving in an unprecedented way, and that the gap therefore represents an imminent threat, every one of those claims would be unsupported, and you would be right to discount all of it, including the part that is true. The true part is narrower and more durable. This is a very active boundary that produces large earthquakes routinely. Today's event was routine, and routine activity on this boundary has, for 108 years, gone around one particular stretch of it rather than through it. That is not alarming, it is arithmetic. So if magnitude is not the thing to watch, and if the count of aftershocks is not the thing to watch, and if today's earthquake was statistically unremarkable in a region where unremarkable means magnitude 6.4, then what exactly is anybody supposed to be watching? Part 14. Migration, not magnitude. The signal is not how big the next one is. The signal is where it is. That is the whole answer, and it took 2 hours to earn it, so let me build it out properly rather than leaving it as a slogan. In the coming days and weeks, the aftershock sequence from June 8th is going to keep producing earthquakes. That is guaranteed. Sequences of this size run for months at elevated rates and for years at slightly elevated rates. There will be more magnitude 4s, there will probably be more 5s, there may be another 6, and if there is, it will produce headlines, and those headlines will be about the number. The number is not the information. Here is what the two scenarios actually look like on a map. In the first scenario, the aftershocks keep occurring inside the footprint that was established in June, the 165 by 150 kilometre zone south of General Santos. Events scatter through it. The rate declines along the Omori curve. Occasional larger events punctuate the decline, and over months the whole thing fades toward the regional background. That is a sequence winding down. That is the normal, expected, overwhelmingly likely outcome. In the second scenario, something different shows up. The event stops scattering randomly through the existing footprint and starts showing a direction. A cluster appears at the northern edge of the zone, then another one slightly further north, then a magnitude 4 or 5 in a place that has been quiet all summer, closer to the segment that has not moved since 1918. That is stress walking. And here is why migration is the right diagnostic rather than magnitude. Stress transfer is a spatial process. When a rupture loads adjacent rock, it loads specific places, and when those places start to fail, they fail in the order in which the stress arrives. So the observable expression of stress moving along a boundary is not that individual earthquakes get bigger, it is that the locations of earthquakes progress in a direction. The beautiful thing about this diagnostic, and I mean that word, is that it requires nothing new. No new instruments, no new science, no breakthrough. Every earthquake above roughly magnitude 4 in this region is already located, catalogued and published within minutes, and has been for years. The observation is just watching where the dots land on the map. That is the entire watch criterion, not a number, a direction. There is a caution that has to ride alongside it though, because a diagnostic this simple invites overreading, and overreading is how people end up frightened about nothing. Aftershock sequences are noisy. They expand and contract at their edges all the time. Clusters appear in one part of a zone for a few days and then stop, for reasons that are often nothing more than the ordinary randomness of where the next stressed patch happened to be. 2 or 3 events at the northern edge of a zone is not migration. It is Tuesday. What would constitute migration is a sustained progression, activity that moves in one direction over weeks, not days. Events appearing in places that have been quiet through the entire sequence, not places that have been intermittently active. A trend rather than a scatter. And crucially, it is something you assess retrospectively over a window, not something you declare from a single map on a single evening. So if you're following this, and I hope some of you will, the discipline is to watch the pattern over weeks and resist reading meaning into any individual event. The single earthquake is never the story. The direction of the population is. So let us reassemble the whole argument, because we have travelled a long way from a bulletin at 12:14 in the afternoon. An earthquake struck off southern Mindanao. The first solution put it at magnitude 7.0, 258 kilometres away in effectively Indonesian water, and that solution was an automatic one, produced in minutes from first arrivals with a one-sided station geometry, and it was wrong in the way automatic solutions are characteristically wrong. The reviewed solution moved it back to 37 kilometres southwest of Balut Island, in the island municipality of Sarangani and Davao Occidental, a different place entirely from the Sarangani province that June devastated, roughly 100 kilometres away. And it dropped the magnitude to 6.3 or 6.4, which is a factor of 11 in energy, which turned a hypothetical new rupture into a continuation of an existing sequence. The moment tensor came back, 92% double couple, clean, simple, no volcanic component, no fluid signature, no room for a non-tectonic source of any kind. The compression axis pointed at 255 degrees, matching the direction the Celeb's seafloor is being driven eastward beneath Mindanao. The nodal planes dipped near vertical in pure reverse motion and struck north-northwest to south-southeast, parallel to the trench, thrust faulting on the subduction system, driven by plate convergence, unambiguously. The famous strike-slip faults, the Mindanao and the Philippine, were eliminated mechanically rather than geographically, because a strike-slip fault cannot produce a thrust beach ball, which left 2 candidates and the depth chose between them, 11.5 kilometres against 33 to 57 for the June main shock. Far up dip, not a re-rupture, either the shallow near trench portion of the interface or a splay thrust in the accretionary wedge above it, and an east-dipping solution on a boundary where the Sangihe side dips west, pointing at the Cotabato Trench, and then the gap, 70 to 100 kilometres of that same trench, bracketed by the 2023 7.5 and the June 2026 7.8, silent since 1918, when this system produced a magnitude 8.3, to the north, which is not where today's earthquake was, and the energy accounting, 1/150th of the main shock, almost nothing relieved. There is a thread running through all of that which is worth pulling out on its own, because it is the actual lesson of the day, and it has very little to do with the Philippines. Almost everything that turned out to matter about this earthquake was invisible in the headline. The headline had a magnitude and a place name, and both of them were wrong in the first version and imprecise in the second. The magnitude told you nothing useful, because a magnitude 6.4 in this region is ordinary. The place name told you something actively misleading, because there are 2 of them. What told you anything was the depth, which almost nobody reported, and the compression azimuth, which nobody reported, and the dip direction, which nobody reported. Those 3 numbers, none of which will appear in any news story about today, are the entire content of this event. That gap between what gets published and what is informative is not a criticism of anybody. A news desk covering a magnitude 6.4 in the Philippines has a few hundred words and a deadline, and the magnitude and the place are the right things to lead with for a reader who needs to know whether people are hurt. But it does mean that if you want to understand what an earthquake actually tells you, you have to go past the bulletin into the solution, and the solution is public and almost nobody looks at it. Put together, today's earthquake was diagnostic rather than dangerous. That is the honest characterization. It did not hurt anybody, as far as anyone knows tonight. It probably will not. What it did was tell us 3 things we did not previously know with confidence. It told us which structure is producing this sequence. It told us the system is still adjusting 8 weeks on in parts of itself that June did not break. And it told us, by where it happened, that the segment everybody is watching did not participate. June 8th changed the stress field beneath southern Mindanao. That is not an interpretation, that is a mechanical fact about what a magnitude 7.8 does to the rock around it. 2 months later, the crust down there is still working through the consequences, and today was one of those consequences arriving on a piece of fault that had been sitting quietly underneath the whole thing. It is almost certainly not the last one. There is one more piece of this worth watching over a shorter timescale, and it arrives faster than any of the tectonics. Over the next 24 to 48 hours, damage reports will come in from Glan and from the towns along that coast, or they will not. Fivolk said no damage is expected, and the models behind that statement are sound for buildings in normal condition. The buildings in that corridor are not in normal condition. Whether intensity 5 shaking into 8-week-old cracks produces reported damage is a small, concrete, checkable question, and it will have an answer before the end of the week. That answer matters beyond southern Mindanao, incidentally. Every earthquake sequence in a region with damaged building stock runs into the same gap between what the models assume and what is actually standing. If a magnitude 6.4 produces damage that a magnitude 6.4 should not produce, that is a data point about cumulative vulnerability that applies everywhere sequences run through populated areas, which is most places, and I want to end where this actually lives, which is not in a moment tensor. It lives in Glan, where people felt strong shaking today in a town that buried its dead in June. It lives in General Santos, a city of more than 700,000, where the walls have cracks in them that nobody has assessed. It lives in the island municipality, out where the land breaks up into Balut and Sarangani, closest of anyone to where the seafloor moved this afternoon. It lives in 121,300 homes that were damaged or destroyed 8 weeks ago, and mostly have not been fixed, occupied tonight by people who have now been shaken twice, and who will be shaken again. There is something particular about the psychology of living inside an aftershock sequence, and it is worth naming because it is the actual daily experience of tens of thousands of people right now. It is not the fear of a single event. It is the absence of an ending. A hurricane arrives and departs. A flood crests and recedes. An earthquake sequence has no schedule and no closing ceremony. It just gradually becomes less frequent, over months, without ever announcing that it is over, and the people living inside it have to decide for themselves when to stop bracing. Some decide too early and move back into weakened houses. Some never quite decide and stay braced for a year. Neither is irrational. There is no correct answer because nobody can tell them when it ends. Today, at 14 minutes past 12, every one of those people had to make that calculation again. None of those people can do anything about a fault. That is the part of this that sits badly, and I am not going to dress it up. There is a stretch of rock 70 to 100 kilometers long, several kilometers below the seabed, that has been accumulating strain since 1918. It does not know it is being watched. It does not respond to preparation, or to attention, or to concern. The only thing it has done for 108 years is wait, and the only thing anybody can do is be ready for the day it stops. So here is the question I am leaving you with, and it is a genuinely answerable one, which is rare in this field. Over the coming weeks, the aftershocks from June 8th will either keep decaying inside the footprint they have occupied all summer, or they will start stepping north. Nobody needs a new instrument to see which. Nobody needs a model. The earthquakes will be located and published as they always are, and the dots will either scatter or they will march. If they scatter, this sequence is ending the way sequences end. If they march, then the 8,500 earthquakes since June were not the story at all. They were the approach. Which one is it going to be?